With Neptune raising concerns among scientists and space fans, something very similar has been noted. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alerts about the potential results of this glorious clash. Yet, how did Pluto end up on a collision course with its faraway neighbor? And what could this limitless accident mean for us here on Earth? Could we research this spreading out event? Once remembered as an unquestionable planet, Pluto was reclassified as a dwarf planet due to its unique orbit. Despite this change, it continues to excite and attract stargazers. Continuous estimates from unquestionable specialists highlight a concerning overlap between Pluto's path and that of Neptune. These trained professionals warn against a possible collision between the two planets, which could pose a serious risk to Earth. Pluto's journey around the Sun is distinguished by its exceptional characteristics within our planetary system. Its orbit spans a wide 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the significantly elongated shape of its orbit, deviating from the near-circular paths of the major planets. Furthermore, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making it much more extreme compared to other planets. One notable aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. So, why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational influences exerted by other planets. The study of Pluto's orbit began soon after its discovery, presenting a perplexing challenge for astronomers. Unlike most of the planets whose orbits are relatively close to the ecliptic plane, Pluto's distinct features include a considerable inclination and an elongated shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's path. The stability of Pluto's orbit, despite these complexities, serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three massive bodies, such as Pluto, Neptune, and the Sun. This issue explains the complicated interplay of their trajectories and gravitational forces. Terms like asynchronous libration, latitude libration, and the VZK effect contribute to unraveling this celestial puzzle. Astrophysicists assert that asynchronous libration, responsible for keeping planets in their orbits, plays a key role in the relationship between Pluto and Neptune. This term refers to the fact that when Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune, preventing potential collisions. Latitude libration ensures that when Pluto approaches Neptune or other giant planets, it is positioned far above or below their orbital plane, providing an additional layer of protection against crashes. The VZK effect explains why Pluto's orbit around the Sun appears erratic yet remains stable over time, despite apparent irregularities. Mathematical simulations in the late 1980s revealed that, while not perfectly stable, Pluto's orbit is chaotic with minor initial deviations, leading to significant differences over millions of years. However, Pluto's unusual orbit maintains stability over extremely long timescales, keeping chaos in check. Recent computer models have enhanced our understanding of how massive planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto's, adds to the stability of Pluto's orbit. Likewise, Jupiter's immense gravity plays a significant role, while Saturn's smaller influence also contributes. Through comprehensive simulations, scientists have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining order and consistency in the universe. Without these elements, the solar system would be prone to greater chaos and unpredictability, potentially leading to collisions or ejections from stable orbits and causing increasingly widespread impacts on other celestial bodies. Understanding Pluto's orbit is particularly important amidst discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the unique nature of the solar system. Pluto's case highlights how seemingly unstable orbits can achieve harmony through the complex interaction of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are crucial for gaining a deeper grasp of our position in the universe. Exploring the depths of space often reveals the unconventional nature of celestial bodies, and Pluto's orbit serves as a prime example of this whimsy. The concept of orbital chaos vividly illustrates the delicate dependence of a celestial body's path on its initial conditions, as shown in Pluto's case. Even slight variations in a planet's position or velocity can drastically alter its long-term orbit. Computer simulations have been instrumental in helping experts understand how Pluto moves through space. By making small adjustments in these simulations, astronomers can see how minor changes can have a significant impact on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's path. Despite features like asynchronous libration and latitude libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a slight initial difference in Pluto's position or velocity can lead to substantial changes in its path over time. Various years notwithstanding this innate confusion, Pluto's circle stays stable for a remarkably extensive period of time, loosening up over billions of years. This suggests that, underneath its obviously inconsistent appearance, Pluto's journey around the Sun follows a coordinated order. Expecting vainglorious events, especially with planets like Pluto that have strange orbits, the characteristic uniqueness of these systems makes long-term predictions uncertain. Numerical simulations help us understand and anticipate the future movements of celestial bodies. However, they also reveal the limits of our predictions. These models heavily depend on accurate initial conditions and replicate complex interactions. Even a small mistake can lead to drastically different results, making precise forecasts problematic. The chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our still limited knowledge. The immensity of interstellar distances and the scarcity of planets in open space act as barriers against constant influences. Moreover, rogue planets are generally rare compared to the number of stars and planets in stable orbits, making such encounters much less likely. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how each planet's presence and position can influence the stability and direction of other bodies in the system. Despite these complicated forces, some astrophysicists are expressing concerns about a possible collision between Pluto and Neptune. This raises questions about why such a collision, which seems fantastical given these complex dynamics, is still a subject of concern. Neil deGrasse Tyson, a renowned astrophysicist, offers an insightful perspective on the mysteries of our solar system, particularly concerning Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet instead of a full-fledged planet, shares thoughtful reflections on how our understanding of celestial mechanics is constantly evolving. Tyson views Pluto's reclassification not as a demotion, but rather as a key acknowledgement of our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes that the allure of these questions is what makes astronomy so fascinating. He also understands how space-related events and discoveries impact public interest in space science. He sees occasions like Pluto's reclassification and its unusual orbit as opportunities to capture the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes odd aspects of space mechanics, Tyson aims to foster a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a window for the general public to marvel at the wonders and mysteries of the universe. Working alongside other researchers, Tyson actively warns the public about the possible risk posed by Pluto's eccentric orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could represent a genuine danger, suggesting that a collision with Neptune is long overdue. Furthermore, Tyson highlights how such a collision could disrupt the balance of the solar system and lead to catastrophic consequences, potentially even affecting Earth. An impact between Pluto and Neptune would be a rare and unsettling event in our solar system. This collision would release a massive amount of energy, possibly destroying Pluto, due to its smaller size and cold composition. Debris from the impact could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specific details of the collision. Michio Kaku, a prominent theoretical physicist known for his work in string theory and scientific innovation, offers an interesting perspective on this scenario. His views on the future of space exploration and the relationship between celestial mechanics and theoretical physics provide valuable insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies, like Pluto, can offer essential insights for future space missions. This knowledge can help navigate the solar system more effectively, anticipate potential dangers, and plan missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the models derived from studying Pluto's orbit can be applied to examine other celestial bodies, providing a framework for approaching and understanding distant worlds. In examining the physics of planets, Kaku often highlights the vital relationship between celestial mechanics and theoretical physics. Actual science believes that the improvements and participations of planets, like the gravitational dance among Pluto and Neptune, are not detached events. However, they are associated with fundamental principles of actual science. Kaku's work in speculative material science, especially in string speculation, points to understanding these principles and more. That's what fundamentally he recommends, considering the complexities of heavenly mechanics. For example, the orbit of Pluto can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also kept an eye on the possible effects relating it to his hypotheses about the universe, expecting that if Pluto and Neptune were to influence it, it would be a significant event in cosmology, offering a momentous observational opportunity that could perhaps add to our understanding of string theory. String speculation, a theoretical framework replacing point-like particles with one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. The collision of such scale in the nearby planetary system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extraordinary conditions. A critical aspect of string speculation is that the gravitational waves generated by the impact could provide significant data for testing assumptions about string theory related to gravity and spacetime. While the immediate impact on Earth would be negligible due to our distance from the outer nearby planetary group, the broader implications of such an event could be significant, potentially contributing to our understanding of the central nature of the universe, as described by string speculation and various areas of speculative material science. Pluto's orbit serves as a striking example of gravitational mechanics, demonstrating both stability and chaos within our nearby planetary group. The unique characteristics of its orbit, impacted by the gravitational forces of neighboring planets, particularly Neptune, highlight the complex and dynamic nature of space. The universe holds many secrets, and the three-body problem is just one of them. There are other potential calamities that scientists anticipate. While the possible outcomes of planets colliding in space are extremely low, it is not entirely inconceivable. The way planetary orbits are affected by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems, like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythmic configuration brought about by orbital resonances. Over time, these patterns can make planetary paths less stable, potentially provoking collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently happening. Researchers eagerly monitor these systems to understand how planets affect each other's paths, particularly when they are close. This data helps us appreciate the evolution of planets in space. Rogue planets, floating through space without orbiting a star, present an additional intriguing element. These planets, once part of a star system, are ejected due to gravitational disturbances or other celestial events. For instance, the close passage of another star or dynamic instabilities in other systems. Over the long haul, these wandering planets can traverse enormous distances, potentially arriving in regions far from their original point during their solitary journey. There is a chance of them encountering other star systems, if one of these rogue planets enters another nearby planetary group, there is a slight possibility of a collision with a planet in that system. However, given the vast and predominantly empty nature of space, the likelihood of a rogue planet directly impacting another planet is very low.